plug this into the formula for the covariance and then solve basically for what is the W that makes this equation equal. Well, it's mathematically tedious, right? So you wouldn't do that on pen and paper, but if you use Excel, there is a function that's called Gold-Seed function. So it's basically trial and error by the computer. Right? So you let the computer, you give the equation as a condition, you let the computer solve that for you. And the computer will just spit out the correct portfolio weights that solves this equation. Right? So that's a way of mathematically solving this. So this is kind of true for any tangency portfolio, and not only in the capital asset pricing model, but it will be kind of, we're going to use this to derive the formula for the capital asset pricing model. Right. Suppose this was not the case, so I'll give you a little bit of an intuition behind this. Maybe look at two different stocks which have the same covariance to the tendency portfolio, so the same variance contribution to the portfolio, but maybe have different excess returns. So what could you do? You could lower the share that you have in the one with the low ratio and increase the share in the one that has the higher return. Right? Because they have the same covariance in that example, you wouldn't change the portfolio variance, right? But you would increase the return of the portfolio, so you could do better. Right? So if you can improve by doing that, right? Decrease the share in the low return portfolio and increase the share in the high return portfolio, you've improved. Right? And if you can improve, well, then you have not been on the capital market line in the first place. Right? So the capital market line is the one with the highest slope in the picture, right? So it must be kind of the best line already, right? So you cannot improve beyond that. Right? So this kind of little example that I gave you is not feasible if you already have the correct capital market line. Right? So you cannot improve beyond that. So that's kind of a little bit of an intuition behind it. Not quite sure if I have defined this already, but I'm going to use this term quite extensively because it's also used in empirical research. So the difference between the return of an asset and the risk-free rate is called excess return. Sometimes you would also call this risk premium, so especially if there is an expected value, then that's the same as the risk premium. But if you measure something in historic data, you would rather say excess return because it's a little bit kind of more agnostic. Not every excess return has to be a risk premium. So that's the idea behind this ratio here. Right? And we can use this to determine tangency portfolios. It's pretty useful kind of if you kind of want to solve this in a computer. Otherwise, kind of finding basically finding the line here which has the highest slope. That's a little bit tricky. I think there might be other ways mathematically to do that. Right, so the slope would be the first derivative of that function, so you could technically compute that, and then you would find the maximum of that first derivative. So compute the second derivative and set that equal to 0. That should get you there. But like, I haven't showed you the functional formulas for this here. It's this hyperbolas. So technically you have a little bit of a problem because you have this lower part of the hyperbola and the upper and lower part have different functional forms. It will be pretty messy to do this kind of analytically, and this is kind of a much nicer approach, and the quickest one to be fair. Right? If you don't want to use this do this graphically, this is an approach that always kind of is successful. So you should add this here, what you do. So you use this equation, solve for W that satisfies the equation. The first equation. And excellent to do this using the Gold-Seed function, for example. Or you can use the solver, any numerical solution to make it that you want. But this is not all. You can actually derive another nice result from this, because this ratio here, this really holds for any asset, including the tangency portfolio itself. Right? So if you write down the excess return of the tangency portfolio, divided by the covariance of the tendency portfolio with respect to the tendency portfolio. That is also the same ratio as for any other stock. And I've kind of written down this derivation here on the next page. Right, so the left-hand side is the ratio for the tendency portfolio, and the right-hand side is the ratio for kind of any arbitrary stock K that I picked. Left here, that's my tendency portfolio. And then here we have kind of any asset. Okay. Right, so those two ratios also have to be the same. And now I just rewrite that in the following form. It's just rearranging this thing. So I want to solve for the expected return of the asset K, which is this here. Then I sort terms, and I use the fact that the covariance of an asset with respect to itself is the variance. Right, I'll just replace that. And we get the following relationship. So the axis return is equal of the asset K is equal to the axis return of the tendency portfolio multiplied by the fraction of covariance divided by variance. Now, have you seen this thing before? That should ring a bell. How did we call that? Yeah, that's the beta, right? So this here is now the beta with respect to the tendency portfolio. So we already have an information about prices that we can derive from portfolio theory. So once you have found a tendency portfolio, then any axis return of any asset will be a linear function of the return of the tendency portfolio, and the beta with respect to the tendency portfolio kind of determines the relationship. This here is the axis return of the tendency portfolio. And here we have the axis return of asset K. And it's important that it holds for any asset if we have the correct tangency portfolio. And the interesting thing here, and I've put this down here since we now have already discussed what equilibrium is, this equation also doesn't hold when the market is not in equilibrium. It holds when portfolio theory is valid. That's why I put it in this chapter. Right? So if we found the correct tangency portfolio, then you can always write down returns in a similar fashion as linear functions of the return of the tangency portfolio, and the beta is determining the relationship. So this is usually a result that's attributed to the capital asset pricing model only. Right? And for some students, you might have seen this relationship before. Let's write a beta in here, and if you've seen the capital asset pricing model before, that's the big equation that we look at in the next chapter. And it's falsely attributed only to the capital asset pricing model. Right? But it is valid already in portfolio theory. It doesn't really tell us where prices exactly should be because it's unclear kind of what the expected return of the tangency portfolio exactly is, right? Because that's also the sum of all the returns of the share. The asset K is in the tangency portfolio, right? So, but that's very, very important. This holds also if the market is not in equilibrium. This always holds. And this is basically one of the reasons also why testing the capital asset pricing model is so tricky, right? Because if you test this here, or this relationship, and that's what you want to test at the end, well, you can still not be quite sure if the market is really in equilibrium or not, because it also holds, this equation also holds if it is not in equilibrium. That's a bit of a problem that we face. So, the reason why I'm discussing this question, these formulas, is also because I want to show you now the formula in the capital asset pricing model, and usually this kind of falls magically from the sky. It appears somehow, and people don't really know where this comes from. Of course, I haven't really told you where this exactly comes from, but I think if you think about the capital market line is already kind of the best line that you can draw, the red line, and you go through this logic, you now have at least an economic intuition behind where this comes from. And by the way, it's the mere fact that you can kind of find a tendency portfolio using this relationship is pretty important. Right, so that's probably something that you don't find in standard textbooks, but I think it's essential to the theory. Okay. Let's see, are there any questions so far? Now then, let's see how this now looks like in the capital asset pricing model. And this is the core equation. It's a little bit differently written down here with our abbreviations. The mu's and the risk rate is usually put on the right-hand side.